bankruptcy of Serbian companies, and in this process we decided to use the self-sufficient techniques. Okay, I'm going to talk about first about models for bankruptcy prediction that we use, then about self-computing techniques, and about Serbian companies' financial data. After about modification of Altman's model that we made, and at the end about comparison of all created models. Well, so first of all, when we decided to deal with this kind of problem, we needed some basic inputs, and we found really several already created models for bankruptcy prediction, and each model uses its own financial data, relevant financial data, and financial ratios. But from these old models, we decided to use three of them. And the first one is Altman's set score model. As you can see here, Altman created the linear combination of 5 different financial ratios here. And when we calculate for one company this set score model, we can then see, based on that score model, where our company is now, in which zone. So, according to Altman, if we have that score model below this border, we can say that that company has more than 60% to bankrupt in the next 2 years. After that, Altman did the modification of the first model, and he created 2 different models. First one for private companies, and the second one for manufacturers, for non-manufacturers and emerging markets. These models are pretty much similar, but you can see here that parameters have different weights. And each model now had, according to Altman as well, had different borders for the zones. Then, third model was Olson's all-score model, and as you can see here, it has more than 5 financial ratios, and based on these ratios, then and calculated all-score value, it's possible to calculate probability that this company is going to bankrupt. But the main thing with these models are that they are created based on financial data from some specific market. And we wanted to see, well, that doesn't mean, of course, that they are not applicable to our companies and to our market, but we wanted to see how well they will perform when we test it on our data, and can we maybe do something that's better and more accurate. In that process, we decided to use self-computing techniques, and that's the main goal was to modify these models, and we decided to use self-computing techniques just because they are really flexible but powerful, and they can solve problems which are not easy to describe with predefined algorithms, and easy to solve with simple techniques and methods. And from among all of self-computing techniques, we used artificial neural networks, fuzzy logic, and adaptive neural fuzzy inference system. So you probably all know, but I will just say a few words about neural networks. Well, artificial neural networks are very much similar like biological neural networks, and as you can see here, they have different layers, and in each layer they have nodes and neurons, and every neuron is connected with neurons from the previous and next layer. So this is just one structure, and the most important thing when we are trying to model our problem and to solve something using artificial neural networks is how well and how precise we are going to develop our model. So in our case, it's important to know how many input nodes we have and how many output nodes we have. So after that, we used the fuzzy logic. Alexander already explained a lot about fuzzy logic. So unlike conventional logic, in fuzzy logic we don't have just true and false values, but we have a value that's between 0 and 1. And fuzzy logic enables us to use linguistic variables and fuzzy rules, so we can say that something is probably true and that's just true or false. So after that, we used Amphis, and by using Amphis, we created inputs and outputs using fuzzy logic, and fuzzy rules we created using neural networks. So Amphis allows you to combine the best characteristics and features from neural networks and from fuzzy logic. So our problem was, and our study was based on financial data for 102 companies. Half of them were active and half of them were bankrupted. After that, we divided our data set into two pieces, one for testing and one for training. Also, we used stochastic cross-validation just in order to avoid any type of dependency between records. And all these data we collected from yearly financial data that every company is obliged to have every year. After that, these are results when we try to apply these models on our data set, and we decided to use only Z1 score, not Z2 score or second one, because our main focus was private companies. And after that, because Altman Z-score had the best results, we decided to use that model and to somehow try to modify it and to make it more approachable but suitable for our companies. And that we use self-computing techniques. So this is just the structure of our application that we created. And on one side we had neural networks, and on the other side we had Amphis structure. And our main input was Excel file with all collected data sets. And after each iteration of experiment and testing, we had database storage, and in which we stored every relevant data for each iteration. So on one side we had neural networks, and there we created neural networks with 3 layers, and we had 5 neurons in input layer. That's because we have in Altman Z-score we have 5 different financial ratios, and just the two neurons in output layer because we are trying to do classification. We decided to try to make neural networks with different number of hidden neurons in hidden layer, because there is no general rule which says in hidden layer you should have specific number of neurons. So we created different neurons, and we used two learning methods. We used backpropagation and repropagation. So these are the best results that we got. So for backpropagation, the best was a network with 6 neurons in hidden layer, and with repropagation with 7 neurons in hidden layer. For Amphis, we needed to implement direct communication with MATLAB, and we used the MATLAB implementation of Amphis. There we created inputs and outputs which were modeled by 3 membership functions. And when we got our results, important questions just pop up, and we didn't know first what to do with results, because they were not in Altman's Z-score interval. And first we did that we decided to just create a logical border based on initial values, and afterwards we decided to do linear transformation of all results and to get results which are in interval from 1 to 0. And with linear transformation of results, we got better results. And this is a better result for Amphis and the hybrid method. these are the best and the worst results because we had networks with 8, 9, and 10 of course different hidden neurons. So the best result was with neuronal network with backpropagation and with 6 hidden neurons. And the worst result was with AMPHIS and hybrid method and without transformation of results. So this model was successful in only 60% of the cases. So to conclude everything, we collected the financial data for 102 survey companies. We are aware of that this is really small data set and that we need to expand our data set in order to get more accurate results. But we had problem with digital data and financial statements for companies because we used digital data for last 4 years and only that is currently available. After that, we modified Altman's Z-score model using AMPHIS and neural networks, and we got the best results by using neural networks with 6 hidden layers and backpropagation method. So our future work is, as I said, to expand data set and to see where we stand with our results and with our created and implemented application when it comes to bigger size problems, and to compare our results with different techniques, maybe with support vectors machine or other technique that's applicable for this kind of problems. So that's all, and thank you for attention. And if you have maybe some questions, I'll be more than glad to answer.
I have some questions.
Ladies first.
Yes. First, I didn't understand very well in the results that because you said that it will give you like if they are on the gray zone, on the distress, etc. And here you are showing just like a single result. So you are.
Oh yes. Well, we tried to calculate how successful we were. Well, if one company based on Altman's Z-score is going to bankrupt, and we had in our data set. We had companies that already bankrupt, and we had companies that are still active and working. So we tried to look 1 year back and to see if our model predicted good enough for this year.
Okay.
So we had the company that bankrupted from last year to, well,
so
not from last year, but 2 years back until now, then we decided that that's a good result.
Okay, so you validated with the ones that were already gone.
Yes.
So you were not looking for the gray zones or anything, you were looking more to the ones that already
but already bankrupted and which are still active.
Okay, second question is that I didn't understand did you try a fuzzy root system or you just did the AMPHIS and the
No, I talk about fuzzy logic because in AMPHIS, we created,
but
we
you did not do a fuzzy root
no,
system?
not
You
fuzzy
just
logic
did the
system, but
AMPHIS
we,
and
in AMPHIS we used fuzzy logic and we created our own membership functions and modeled our input and output data. But for rules, we used neural networks.
Okay.
I have one question also. I'm coming from a company working with financial data, so we are offering for you to expand the data set.
Oh, great.
So on the other side, what we are hearing from, let's say, practical use, you must understand I'm an ex-student of the faculty, but now I'm currently working directly with the banks doing the scoring for businesses. So what we see generally, the main reason for bankruptcy is the connected companies in Serbian system, because you can close one company and open another one. So the risk is coming mainly from this system, because the system allows this. I don't know Are those
how it
companies
reflect on data
only
sets.
single companies or the, let's say, group of connected companies?
Yes, unfortunately, in our data set, we would have these companies which are connected as well single values. So we would have two records for companies which are connected. So it probably we could have some maybe 6th or 7th, doesn't matter, input in our application, in try to have some flag or something like that, which will single us to which would be signal for us just to know that maybe that company is connected with some other company from data set. But yes, that was really really big issue as well as how long the whole process of bankruptcy is in Serbia.
So just would like to share the contact with you, and then we can another, let's say, a meeting or something. Thank you.
Dear colleagues, distinguished professors, ladies and gentlemen, my name is Radojević and I'm here to present our paper, Modeling Complex Systems using Multi-Boolean Algebra. The focus of our paper is Boolean networks, and they are consistent real-valued realization. As we all know, Boolean logic is two-valued logic, and we try to offer a generalization of Boolean concepts and Boolean networks using multi Boolean algebra and with that called generalized Boolean networks. First, I will give a short, brief outline of classic Boolean networks, and then I will talk also briefly about multi-Boolean algebra. Then I will show the contribution of this paper, generalization of Boolean networks using IBA, and I will try to give you an illustrative example of our model. First, we need to define the complex system. There are many definitions of complex system, and here we assume that complex system is a system with a large number of interconnected elements or subsystems, and that system is highly nonlinear. Complex systems are usually adaptive, and their dynamics is very hard to assess, so we use soft computing methods for that problem. The most common example of the complex system are biological systems such as the brain, immune system, genome, protein system, synthesis problems, and so on. Also, stock markets can be, for stock markets we can tell that there are complex systems, organizational systems, social networks, and so on and so on. As I previously said, dealing with complex system is a very hard problem, and there are conventional methods for dealing with complex systems, such as system decomposition and simulation methods, and there are also computing methods for dealing with assessing complex system dynamics, as neural networks, self-organizing maps, evolutionary algorithms, etc. Here we focus on the logic-based approaches for modeling complex systems because we want to assess the causal interactions research about modeling complex system using logic is has been done during the last 50 years, and it is very intense and very popular subject even now. Here, the classic concept of modeling complex system using logic is with Boolean networks. Boolean network is a directed graph with the set of nodes that represent components, and the values of nodes represent the states of the system. And set A, that is a set of direct edges that present interconnection between elements, and we assume that the interconnection is logical in this case. Logical not as based on logic. The dynamics of a complex system is presented with this set of equations. The state of the system in xi is defined with function fi, that is a function of the values of the states of all system in previous moment. And here fi is Boolean function that is two-valued, it can be only 1 or 0. Here we present dynamics of a certain Boolean map, and we can see that all values goes to attractors that have values 0 or 1. Boolean networks have clear-cut meaning, they are very easy to interpret, so the most decision makers like this approach. Here we will address two questions regarding Boolean networks. The one is the validity of dynamics. In classic Boolean network, it is secured because the classic logic follows Boolean laws. And the second is values. So classic Boolean networks are two-valued networks, and they are adequate for switch-like interaction on and off, true and false, 1 or 0. And there is no room for gradation because we have only two values. So we address this as a problem because with two values there are very small descriptive power, and the logic and the following decision for us is to incorporate fuzzy logic in Boolean networks. I will not talk about fuzzy logic now, Alexander here outlined that. With fuzzy Boolean networks, we have values of unity interval that are offering great descriptive power. Instead of classical logical connectives and or, we use T norms or S norms. And we have a problem when we use classic fuzzy logic in Boolean networks because the validity of dynamics is not secured. Why is that? Because in fuzzy logic, laws of excluded middle and contradiction are not followed. And we think that that's a crucial problem with fuzzy logic in Boolean networks. And the solution for that is introducing interpolative Boolean algebra by Professor Radojević. Interpolative Boolean algebra is consistent unit integral valued generalization of classic logic, where all Boolean laws are satisfied. I will not bother you with mathematics behind interpolative Boolean algebra, but I will gladly speak with you about this problem after the presentation of coffee breaks. But here I want to outline this, that is true, that interpolative Boolean algebra is two-values logic. The first step, we have to transform logical function into generalized Boolean polynomial. Generalized Boolean polynomials are polynomials where we have standard plus, standard minus, and generalized product. I will speak about the generalized product a little bit later. And in the second step, generalized Boolean polynomial are calculated. First, we change generalized product into operator we concluded that this approach is very good for modeling a system when we need to include the gradation, because this system is zero works on the interval between 0 and 1. Logic expressions are transformed to GDPs according to transformation rules. Also, we have a program that automatically transform the logical expressions to generalized Boolean polynomials, and this approach is also offering a great descriptive power. The second contribution, that the validity of dynamics is secured by the Boolean laws, because IDA follows the following Boolean laws. And here I want to present an illustrative example. This is Kobayashi and Hirashi presentation of WTNA5 protein synthesis. That is a system with only 7 nodes, but this approach is suitable even for big data problems. I use this example only for illustration purposes. And we want to compare our approach with conventional fuzzy approach in 3 cases where T norm is minimum, T norm is product, and T norm is Radojević operator. As you can see in these slides, the dynamics of our approach, a conventional fuzzy logic Boolean network, is very, very different, and even attractors are very different. That is also for product T norm and Radojević T norm. And to conclude, our approach to generalized Boolean networks are preserving the logical structure of classical Boolean networks. It is preserving the validity of dynamics, because we use IBA as a framework, and it preserves the possibility of quantitative analysis. Unlike the classical approach, this approach offers a great descriptive power, and for future work we aim to apply this for practical problems in order to assess the results. And we want to deal with the problem of GBM identification. We want to identify first logical expressions in nodes according to data, and the second problem that is much harder, we want to identify the whole GBM structure according to data. Thank you.
Can you go back to your example?
Okay.
Okay, I didn't.
This?
Yeah. I didn't understand what are the lines, all these X1s and X2s and so
Okay.
on. Maybe you should have explained.
On the x-axis,
Yeah.
we have the timeline. This is the first iteration, second, third, how the signal propagates through our networks. And on the y-axis, we have the value of each node, each color.
So the of each node you are talking about the edge, on the value on the edge,
The value of the network
or in the network.
in the node.
In the node.
In the node,
Okay.
because every function corresponds with the node,
Okay.
not with the edge.
Not with the edge.
Yeah,
Okay.
with the edge. And here we want to
So you are
show
not counting if they have like both ways. You are just counting like
directed
directed one.
only one value, and we want to only show how the signal propagates through our networks through time.
Okay.
That we consider as the dynamic of the
Of the network. Okay. Now I understand. Another question. So you said that you also tried with the product other S norms and T norms.
Yes.
And where do we see this in the example?
In this example, as T norm is used only minimum
Oh,
function.
that is for the mean. Okay.
Yes. And for this
Here it
this
is the
function, we
product.
only use
I was lost in the thing because I didn't understand the example.
The
But
graph.
now I see here it's the product.
And we can see also in this slide that for the product norm, we need more iterations to assess which are the attractors due the characteristic of product T norm. And for this Radojević T norm and for minimum T norm, we only
but I don't know if he obeys all the laws or not in terms of what
If
he
they handle well, how he norm is between minimum and drastic norm.
Yeah, it's a kind of, yeah. But it
It's not
has a
suitable.
parameter for you to, so it's not suitable?
Not suitable if
No,
it is
it's not suitable.
Ah.
Suitable for the logic.
Okay, because of the
Yes,
logic.
Yes.
all for function must be non-negative.
Okay,
This is constraint.
okay.
As a consequence of this constraint here between mean and max.
And the max, okay.
Yes.
Thank you.
Thank you, Barbara. And last paper is evaluate order your relation in the engineering reliability by managers.
Hello, I'm Radojević, and I'm here to present our paper that applies the IBA-based order relation in reliability engineering. So, just to go first to the context of this presentation. So, in the first part that we're going to analyze is the basic reliability concept, just to introduce some basic concepts that we are using in our paper. Then we are going to discuss the concept of system signatures and tail signatures. And we are going to introduce cardinality indices, and we are going to discuss their relation to the signatures of the system. The next part is we are going to introduce interpolative Boolean algebra that already Pavel and Alexander talked about, and we are going to introduce an order relation in interpolative Boolean algebra and its application to rank the systems based on their tail signature values. And finally, because the relation in general case, the order relation cannot establish order between all signature vectors, we are going to introduce a logical aggregation of those signature vectors. So now the first thing, I'm basically going to assume that most concepts of reliability engineering are well known, so we are going to just address some concepts that we are using now in our paper. So the first thing is the system structure functioning approach. It is the most common approach in reliability engineering. And the problem with this approach generally is because it grows exponentially with the number of components. So it is inherently a big data problem. But generally, as I said, it isn't so it's just a mapping that associates the vectors of the state vectors of the system to the value 1 if the call system is working, or value 0 otherwise. So basically, we're going to introduce the concept of coherent system. It is a system that contains no irrelevant components, and its structure function is monotone. The monotonicity here guarantees that if we repair one component, the reliability of the whole system is not going to be reduced. So it's a logical assumption. So also the two other concepts that are very commonly used in reliability engineering are path set and cut set, and basically path through the graph of the system, if we are going to speak in these terms, is every set of components for which the system is working. Minimum path set is such path that contains no other subset sets of components for which system is also working, and accordingly minimum cut set is that such set that system fails when all the components within that subset are failed as well in that state. And the minimum cut set does not contain as well as minimum cut set any subset which is also a cut set. So basically the next thing is a concept of system signatures. It is a concept that was introduced by some year ago. Now, as I said, approach based on a system structure function is an exponential, and system signature is a concept that attributes that sort of gives a value to every component, so that actually it reduces the problem to an n-dimensional vector. So basically, although this concept is not as general as system structure function approach, this concept also retains the information about the structure of the system. Now, there is one assumption that we have to assume in this case, and that is that the lifetime of the components are independent and identically distributed. So in this case, the signature of a system is an n-dimensional probability vector whose each element is an order statistic. Basically, it means that if it is a probability under, of course, IID assumption that if component of the system is going to fail, that failure is going to cause the failure of the whole system. So, as I said, this, of course, this is not as general approach as the system structure function, but because it is not accounting the reliabilities of individual components within itself, but basically it is assuming that a probability of failure of every component is equivalent, and like I said, it is identically distributed. So basically, what is the purpose of this approach is to compare the system designs. So let's suppose we are having a couple of different systems of the same orders. We are going to try to assess which system provides better or performs better in terms of reliability. So there is some of the properties of the system signatures is basically that we could, if of course the T here is the survival time of the whole system, we could the sum of the signatures and the expected time of the system failure, or the probability that the if or the statistic is bigger than the time of failure of individual component. I don't know if I explained this well, but basically we could assume that, as seen by the next equation, that that sum of signatures and expected time of failures is equal to the expected time of failure of the whole system. So now we are going to introduce the concept of tail signatures or cumulative signatures. Now, if we spoke about the signature itself, they are related to the failure of individual components, or whether the system, what is the probability the system will fail if that components fail. Now, with tail signatures, we have, it is actually an assumption that if k components fail, what is the probability that the whole system will fail? And as we can see here, the tail signatures are actually the cumulative sum of the signatures of signatures values before that. It can be shown here. So, which now we have to introduce another concept, which is kind of related to the concept of system signatures, and that is the concept of cardinality indices, which are first introduced by Jaeger for application in Debster-Scheffer belief structures. And cardinality index, as you can see this formula here, basically we could interpret this cardinality index as an average gain of certitude that is gained by adding an arbitrary element to an arbitrary set of k elements. Now, this property itself of the cardinality index is going to be very important later when we introduce our logical aggregation for this evaluation for the signature vectors of whole system. Now, basically, the most important thing about cardinality indices and the signature vectors of the systems is that they are basically, as you can see here, they're basically the same values, but ordered. One is ordered in relation to another. One is ordered from the beginning, the other is ordered from the end. If that is clear from this. So the next thing here, just sorry. So Pavel and Alexander already spoke about interpolative Boolean algebra. It is consistent realization of real value logic, so that all Boolean theorems and axioms are preserved. So in contrast to the concept of truth functionality that conventional fuzzy logic has been relied upon, the IBA is a concept that introduces structural functionality where the logical operations are not performed on the value levels by T norms or S norms, but are performed on a structural level. And in this case, the T norms and S norms are only arithmetical operators, not the logical operators. That is the biggest distinction between the classical fuzzy logic and interpolative Boolean algebra. So, in order to establish order relation between tail signature vectors of different systems, we're going to introduce IBA implication. Now, as I said, the signature vectors itself are fuzzy logic values, so within there lies the principle why we're using this. IBA implication is defined by logical aggregation that is called generalized Boolean polynomial. And so here we can see the expression for IBA implication in in this case, now this operator, as I said, is a generalized product that can be between minimum and Lukasiewicz T norm, as we already stated. Now, in our case, because we are comparing two objects that have the same property, we are going to use minimum as the T norm. So this is basically three very simple examples that we are going to try to apply this concept to. So the first, as you can see, the first is the series system between one component and the two components that are in parallel connection. The other system is 2 out of 3 good system, which is also known from standard reliability theory. And the third system is parallel connection between 1 and 2 components. Now, as we already established, by the cardinality indices, and we could determine the signatures of these 3 systems, and we can apply our implication as an order relation between those systems. Now we are first going to compare the first and the second system, and we are going to see that actually the second system is more reliable than first. Now, as I said, in general case, it is not always able to establish an order between 2 signature axes, and that is the rationale for introducing the logical aggregation. So basically, the purpose of the logical aggregation is to coalesce, to fuse different values of some logical attributes, or in our case, the components, into one fuzzy value that will represent them. Basically, we can see that this is sort of mapping from n-dimensional to the scalar value. So we are going to use weighted sum approach. Now, this is our, so I will try to explain. So, in just to make sure we are comparing these 2 systems, because this one has already proven to be better than the first. So, now, what is the rationale for our weighted sum? The first thing about the system signatures is that they are they are actually related to cut sets, or they are trying to determine what happens if one or more components of the system fail. So generally, the first case, which is an empty set, is not something that concerns us, because that is the case when all components of the systems are working. So we're just going to try to assume, for instance, that we are having one system. Now here, this is obviously a Bernoulli variable, and in this case, the signature vector is a one-dimensional vector that has value 1. Now, if we are going to introduce another component, a 2-component system, here we have, we are trying to determine whether, how introduction of another component is affecting the whole system. So basically, the second weighted coefficient is going to be related to that fact. Now, if we introduce the third component of the system, as you saw how I ordered the partitive set of the states, is trying to determine, or actually is related to introduction of the third component, and what happens when other components fail related to her. So basically, this is our weighted approach. Now, there was one other approach by Jaeger, where he introduced a logical aggregation which is called studinal character, which is also used for as an aggregation in Dempsey-Sheffer-Billy structures. Basically, what we are trying to do, our advantage is because our sum of weighted coefficients is equal to 1. Jaeger's sum is not equal to 1, which is a bit strange thing, but he proved. So basically, if we apply this logical aggregation to our signature vectors, these are the values that we get, and basically this means that the third system in our example is the better system. So, in order to conclude this paper, this presentation, what have we done? We have established order relation within interpolative Boolean algebra that can introduce order between some signature vectors, and in case that order cannot be established, we introduced logical aggregation that has more intuitive rationale than attitudinal character. So actually that's it for this presentation.
I just wanted to ask you, what kind of applications do you think that this kind of work has?
What kind of application?
Applications.
Yeah, well, the application is, as I said, the signature vectors, that concept itself is applying to the treating of the systems as if we are completely excluding the reliabilities of the components. We are just discussing how the connections of the system, which system is better based on the way the components are connected with itself. So basically, of course, as you mentioned, if we have in this type of approach, if we have a serious system of highly reliable components, it's going to perform obviously better than the parallel system of very low reliable components. But basically, we are trying to abstract that level and just to try to determine what kind of structure that is connection between components gives us better performance.
It's because, I don't know much about what you were saying, and it would help, like, if you have like a better example than the little one that you had, or a kind of application that people could understand better. Like, what was...
This is a very theoretical.
Yeah,
this is very theoretical.
And the example is two things, so I was thinking, is this for circuits, is this for what?
No, actually, well, we could say that this for integrated network, but it is not. This concept is not. Basically, this is a very abstract concept, and the purpose of this concept, because the system structure function is like exponential problem. This concept is n-dimensional. It is not. It is a linear problem, and it can be the signature vectors can be much easily determined than the system structure function. And the purpose is, if we have like hundreds or 200 component system, which basically is 2 on 100 or 200, the computation of the system structure function becomes very difficult. So the purpose here is with not that general approach as the system structure function offers, to also analyze the reliability of the system and to try to determine who is better. And as I said, we have components that are assumed to be statistically independent and identically distributed. So that is the assumption of the concept. We are abstracting the level of reliability, and we're just discussing discussing the structural connections between the with the components.